Okay. Sorry about that. I wasn't reading, so my options for which the screen I was cloning to wasn't set up right. Anyway, it wouldn't let me like click it and move it either. I don't get it. At any rate, what we're going to be talking about here today is Taylor series, and the idea is that we're going to have differential equations. Sorry, that should be a capital P. Keep everything capital. Okay. So we're going to be looking at differential equations that come in this form, where, as opposed to what we were talking about last chapter, we're going to allow our function coefficients to be actual functions instead of just constants. Um, and in order to solve that, we're going to need to expand into some different types of techniques for looking at differential equations. And one of those techniques is going to involve assuming that the form of our solution can be written as a power series. And so under that assumption, we can get into a whole nother class of problem solving techniques. But in order to set that up, we want to make sure that we remind ourselves what is going on with power series so that we just refresh that information in our minds. Because it is my experience as someone who's taught this class a few times that most people just kind of survive through the series stuff in Calculus 2. And um, that's kind of a shame because it turns out that that's the most important part of Calculus 2 from the perspective of things that you are likely to see in applications. It is extremely important because it allows us to communicate whatever types of functions we like to specifically computers. Okay, and if we need to approximate something, we can approximate it as a Taylor series and get something that has um, pretty good accuracy as well as very specific information that we can determine about how accurate that approximation is and where that approximation fails to be valid, which are some of the things that we're going to be talking about. Okay, so well, we'll write it as a power series. A power series has the form y of x equals the sum from k equals 0 to infinity of a sub k times x minus x naught to the k power. Okay. We call this the power series about x naught or centered at x naught. Okay. Either phrasing is fine. All right. And in the case where the coefficient ak is equal to the kth derivative of f evaluated at x naught over k factorial we have a special type of power series which is known as the Taylor series. Now, pretty much everything that was covered in the Taylor series chapter back in Calculus 2 is going to be in some way relevant to us. Okay, we're not going to necessarily touch on all of the details, but all that background information matters. All right. So the main reason that it matters is because a lot of the notation that we use for power series is reflected in um, sequence notation. If you remember going through that material, the first few sections covered sequences and used that to establish a lot of theoretical facts about sequences because it turns out that it's relatively easy to prove things about sequences, and then everything about series was done writing those as sequences and then using the fact that we have information about sequences and theorems and can prove things about them in order to be able to talk about series. So that underlying foundation of the information about sequences is something that we can't overlook, even though it's not material that we may often interact with directly. So I'm going to review some of the material. There's a more full review available in the online notes that goes through all these details. The book's review is very truncated, and the material online is expanded if you're really flimsy on some of these details. And there's also a video or two that I think is helpful for putting things in perspective. Okay, so if we have something called a sequence, the idea is that we are making an ordered list. Okay, now, so this is what's known as an infinite sequence. And if it terminates after some set number of terms, it's a finite sequence. All right. Just as a comment on notation, I have a tendency to use k as the indexing variable and n as a like benchmark or like total variable or something. Um, Different textbooks tend to use n and k in both places. All right. Those are the two most common indexing variables. It doesn't matter which one you use. Okay. Um, it's just a label, but do know that if both k and n show up in a problem, that's usually because they mean different things. All right. They could be two different indices because you're talking about multiple series at the same time, or you have a reason to rearrange something to write it in a different form, and you change the index letter to make it more clear to the reader that there's something going on. Okay. But as for now, it's just a label. Okay. We're talking about sequences. Sometimes you'll see something written like this. Okay. What this is saying is that we have the set of all a sub k such that k is in the set of positive integers. Okay, that's equivalent to writing the list with ellipses. Okay, or the most compact notation would be this. Sometimes people use parentheses instead of curly braces. I'm going to use curly braces just due to the fact that we're talking about a sequence, so I want to keep that straight as possible. All right. It is sometimes the case that we will have a function that can be used to represent our AKs. So here we have 1/2 to the k power. You can write this out. So we just plug in some k that happens to be in this list in order to get the values that we want. When we do that, we're going to have a function that is just a set of dots, okay? And what we have, of course, is this sequence that we're graphing in a two-dimensional space. The horizontal axis representing the input value k, and the vertical axis representing the value of the function. The thing that is the most important about this is whether or not the sequence converges. For a convergent sequence, the property is this. I kind of wrote this. I got out of order. Okay, so we have a convergent sequence that converges to the number L if and only if there is a number capital N such that k greater than n implies that this inequality is true for all of the rest of the k's. All right. So basically what that's saying whatever. There's a more clearly stated version of this on the webpage. Basically, you pick an epsilon greater than 0, and then for every epsilon greater than 0, you should be able to find a capital N such that k greater than capital N guarantees that this inequality holds for all of the rest of the k's. So you would have Now, these are supposed to be dots and not a line, but I'm not going to draw a bunch of dots. Okay. You specify an epsilon, and that epsilon will be some narrow band. Okay. You can shrink the band to be as thin as you want, but eventually there will be some point beyond which all the elements in the sequence are trapped within the band. Okay. The smaller the band, the further to the right this moves, but it can always be found. Okay. If this quality fails to be satisfied, then we have what's known as a divergent series. Okay. If we have a divergent series, we can't effectively use it for applications. All right. We need to be able to detect them so that we know when this is going to happen, so that we can throw those out as potential solutions to our problems. Okay. This was the ultimate importance of the convergent test for series that you discussed back in your previous calculus classes, was the ability to detect, when we're talking about series, of course, which are all sequences, but we need to be able to toss those away. Okay. So let us now talk about series. Okay. Let's imagine that we have a series that is going to be represented by this sequence Sn. Okay. We call this a sequence of partial sums. And the idea is that it looks like this. We see here that we have the part over here on the right, which are summations. But on the left, this is just a sequence of numbers, right? All a sequence of numbers is an ordered list. Okay. So when we talk about series, we don't hold this picture explicitly in our head, but all of the theoretical work that was put into this and is going on behind the scenes is based on this idea. Okay, these things are really sequences. It's just that for application purposes, a sequence of partial sums, particularly if we allow this limit to go to infinity, we get something that is useful to us in terms of representing functions. Okay, and then we of course have this notation here, which is a shortcut for referring to sums. Sometimes this is just referred to as summation notation, and sometimes it's referred to as sigma notation, because that symbol is the capital Greek sigma. Okay. Now, there are many types of series that we will interact with, and part of the expectation is that when the really important series are referred to by name, you know what the classifications are. Okay. One such type of series is a geometric series. So here we have the sum from 1 to infinity of 1/2 to the k power. All right, and here we're adding up all of the elements here. Okay. Now, the question becomes, does this converge? Okay. It is, yes. We're gonna show it. Okay. So what we're gonna do is we're gonna say that, sorry, I should write this slightly differently. We're gonna say that this is the kth partial sum. Okay, so we're gonna go up to the value for k here, call it the kth partial sum. And so we can write that out. We're going to get 1/2 plus 1/4 plus 1/8 all the way up to 1/2 to the k power. Okay. Now, there isn't anything wrong also with me because this thing is just a number, right? I can multiply it by 1/2. If I do that, I get this. Make sense? Now, what I want to do with these is subtract them from one another. If I do that, Everything except for that 1/2 and that 1 over 2 to the k plus 1 go away, right? On the left-hand side, this just reduces to 1/2 sk, and this is 1/2 times 1 minus 1/2, 1 over 2 to the k, if I factor all of that out. And the sum of the series is the limit as k goes to infinity of the elements of my sequence, which is going to be equal to the limit as k goes to infinity of 1 minus 2 to the k power. And as k grows without bound, what happens to this? 0, right? So this limit's 1. Does that make sense? So we get this limit is equal to 1, expressed algebraically. But I do want to point out that it's not actually that weird of a result, because I don't think that that line's vertical. Imagine we have a square. Okay? Now, if all of those have length 1 on the side, what's the area of those triangles I just drew? 1/2, right? So that, I'll just write it out again. The sum goes on forever, right? So this is 1/2. I'm just going to have to do it all in one color. Otherwise, I'm going to drive myself nuts switching back and forth. That's 1 over 4, right? One over 8. 1 over 16. 1 over 32. Do we believe that that this adds up to 1? Okay. The other ones aren't as easy to draw. Okay. But you can set up some scheme like this in order to be able to figure out what the summation looks like. Okay. In general, what we will have is that for a series that looks like this, its sum is known. This version is slightly different than the version that we had written on the other page. The other one started at 1. This one starts at 0. And then also, I should have written a K here. So there's a slightly different version of this that you'll see that starts at 1. If this starts at 1, this will be K minus 1. But it's the same expression. Okay. Going back to our earlier expression, there are other types of series that we can discuss as well. I'm just going to list these because they do have some importance, but these are things that can be referred to. Binomial series can be written out. They are indicated by having some expression that looks like this. All right, this is known as the binomial coefficient. If you were to read this, what you would say is n choose k. Has some important applications for statistics and stuff. Okay, that's the idea there. All right, and then of course the other thing that we need to know is Taylor series and a subset of this, which are known as Maclaurin series. Which is what our discussion here in this chapter is about. Okay. For our work in applications, the only things that we want to use are series that are absolutely convergent. The condition for absolute convergence is that if I have a series and I take the absolute value of all of the elements of that series, this one must be convergent. Okay, so if I take this series, which might have negative numbers in it, and I change all those numbers to be positive and then add them together and still get a sum that is less than infinity, I have an absolutely convergent series. This is a pretty strong condition from a theoretical standpoint. Okay. There's a lot more possibilities for things here than there are over here. All right. But turns out that this condition matters quite a bit. This is just a shorthand for the phrase if and only if. So that means that this assertion goes both ways. All right. Now, absolutely convergent is the opposite, in some sense, of something called conditionally convergent. All right. A function or a series that is conditionally convergent converges but not absolutely. A few things here because the nomenclature is a little bit strange. When we talk about absolute convergence or something converging absolutely, the absolute is a reference to the idea of absolute value. Okay, something being absolute as an English word is kind of a strong statement and it has a little bit different of a connotation. So please keep those things straight. We talk about converging absolutely, it just means that the absolute values of the entries of the sum form a convergent series. Okay. Now, this here with conditional convergence is kind of tricky. Um, so a convergent series is one that will add up to a finite value, okay? But it may need those negative numbers in order to be able to add up to something that ends up being finite, okay? But it doesn't have the property that if I take the absolute value of everything and then add them up, that I get a value that is finite. This is not a number theory class or a class where we're going to get into the details of the calculus here. But it turns out that Riemann, yes, the same Riemann, okay? He proved that if you take a conditionally convergent series and rearrange it in the correct way, that you can make the series add up to a different number. In fact, that he proved that you can get the series to add up to any real number you want it to. So there isn't just more than one answer, there is an entire number line worth of answers. All right? Now, if you're building something, do you want the answer to be every number I could possibly conceive of? No. All right? So this is why we insist on absolute convergence for our series, because we have to avoid this problem. Now, in some Calculus 2 textbooks, it's also relatively easy to find online. The proof of this isn't that hard if it's something that you're interested in. So if you want to look that up, feel free. Don't be intimidated by it. It turns out that it's a little bit weird, and you might spend 20 or 30 minutes thinking about it. But the modern version of the proof, the way that it's stated, it's pretty short. It's only a couple paragraphs long. Okay. So in order to get us absolute convergence, we use our best and most powerful tool back from studying series in Calculus 2, which is the ratio test. All right. There's several different conditions here, but the one that we care about is we have our series, and we want the limit as k goes to infinity of the absolute value of ak plus 1 divided by ak to be less than 1. If this is true, then our series converges absolutely. If this limit is greater than 1, the series diverges. And if the limit is equal to 1, then the ratio test doesn't tell us anything. Okay? It might be the case that it converges absolutely, or it can just converge conditionally. Either way, that one point on the endpoint probably isn't going to be important enough for us to worry too much about it. Okay. So, questions up to this so far? Seems all right? Okay. So, getting back to Taylor series, the form of a Taylor series, as I mentioned, is this. So a function f of x is supposed to be equal to the sum from k equals 0 to infinity of the kth derivative of f evaluated at x naught divided by k factorial times the quantity x minus x naught to the k. All right. If x naught is equal to 0, then what we will have instead is this, and this is what's known as a Maclaurin series. So if I say Maclaurin series, that just means that you get to use the easy case of setting x not equal to 0 and have a shorter expression to write out for this. Most of our examples in class are going to be Maclaurin series just so there's less to write, but I do want everyone to keep in mind, and this may end up being a quiz question or something that I put on an exam, that none of the procedure that we're going to follow to solve problems for this chapter, except where explicitly noted, changes if I have some other value for x naught. We're going to use 0 most of the time just because it's less writing, but more or less everything else stays the same. Okay, it's just a matter of, do I make you write the extra 4 or 5 symbols needed for like the minus sign and the parenthesis and all that stuff. Okay. Now, for us in our work, we are most of the time going to, instead of writing this more complicated expression, just write instead a generic sequence term, a sub k. So this is a Maclaurin series version of a power series, just written in a more compressed way so that I don't have to track all of that. Okay. If I want to look at this and expand it out, that's what it looks like. Coefficient times the appropriate power of x. If I had x minus x naught to the k here, that's the only change that happens. Okay. And it may be the case sometimes where I need to write out things so that they look differently. We know that this is true, right? I can list out all the terms and write them all out. Okay. There also isn't anything wrong with me deciding that I want to do this. Okay. And it may, for some of the problems that we're going to be looking at, be necessary for us to do that. Okay. When I refer to this, I'm generally going to probably use the phrase peeling off terms. Right. Do that as just we will, part of our problem solving technique for this chapter is going to involve manipulating series in this way in order to get these different types of results. Okay. So if we're going to talk about convergence, specifically absolute convergence, let's take the series, the sum from 1 to infinity of x plus 1 to the k power. And then in the denominator, we're going to have k times 2 to the k. All right. The ratio test says that we want this to be less than 1. Okay. Now, I want to be clear about something. Whenever this formula is written down, we tend to use AKs, and whenever our series are written out, we tend to use AK to indicate the coefficients for the power series. Okay. This AK means the whole thing. All right. So it is important to be mindful of that. All right. And then also, dividing is the same thing as multiplying by the reciprocal. So since this expression is complicated enough, I'm just going to go ahead and write it as multiplication by the reciprocal to save us a little bit of space. So this is AK plus 1, and this is 1 over AK. Now what we're going to do is we're going to start simplifying this because we want to figure out under what conditions is this less than 1. Looking at this, I have k powers of this down here and k plus 1 powers of this up here. So I'm going to be left with 1 extra power of k. Or sorry, one extra power in the numerator. Here, I'm going to end up with 1, 2 in the denominator after I simplify this. And then I'll also have k and k plus 1. All right, now, I hope we all believe that the absolute value of a product is equal to the product of absolute values. This one's fine, okay? And also, x plus 1 and 2 don't have anything to do with this limit. This limit only cares about k, right? And I can drop the absolute value on the inside because that's going to be a large positive number. If you write the absolute value, it's fine. It's not going to change anything. What's this limit? Okay, how do I do limits with infinity over infinity? You use L'Hopital's rule, right? What does L'Hopital's rule say? Derivative, differentiate the numerator and differentiate the denominator, and then take the limit of the new quotient, right? So if I do that differentiation, I'm going to get, it's going to be 1, right? Okay. And of course, the thing that we care about is that this whole thing be less than 1. Okay. So I reduce my expression to something that looks like this. X minus x naught in absolute value is less than r. That capital R is the radius of convergence. If I need to talk about it, the interval from x naught minus r to x naught plus r is the interval of absolute convergence. Okay, normally it's just referred to as the interval of convergence. And depending on whether or not you check the endpoints, one or more of the endpoints might technically be included in the interval of convergence, but we don't get those easily from the ratio test. Generally, we're not going to worry about it. Okay, but technically you can evaluate the endpoints to see whether or not they work. But conditional convergence isn't good enough. You need them to converge absolutely. Okay. All right, so once you have a power series solution to your expression or your differential equation, this is one of the techniques that can be used to verify the range of values for which that solution is valid. Okay, almost all of the solutions that we find to differential equations are going to have some kind of limited radius in which they work. Okay, so that's something that we're going to have to pay attention to. All right, as an example, if we take the expression that we had okay, so what I've done is I've created a function out of the example that we just looked at. Okay, and as we increase the number of terms in our partial sum, we see that we get a function that's being approximated by what's going on here, right? Now, our expression said that x plus 1 less the absolute value of x plus 1 is less than 2 was the range of values for which this worked, right? So we take -1 because it's x minus x naught, right? And then we go 2 to the left and 2 to the right. So we should have x equals -3 and x equals 1. Okay. And if we change these values to indicate what should be that radius of convergence, and we continue to increase the number of terms in our series, does the part of the function in between those bounds change very much? It doesn't, right? So that indicates probably convergence, right? It's very stable within those bounds. But outside of those bounds, especially on the left, we see that there's some wild behavior. Okay, the tail shoots up or shoots down based on whether or not the number of terms is even or odd. Okay, so definitely for values of x that are less than -3, this approximation is absolutely worthless, right? But with 20 or so terms, we see that it's extremely stable for the band between -3 and +1, which is the one where it should converge. Okay, so when we come up with our series solutions for our expressions, this is what we have to be mindful of. Okay, it expires outside of a certain band of values. Okay, and the simplest way to evaluate that is by using the ratio test. All right, make sense? Okay, so we have a little bit of time left, so we'll preview what the next couple of sections are going to look like in asking the question, how do we solve ODEs? Okay. So we'll start off with a relatively simple example here. Okay. And the idea is that we're going to make the assumption that our differential equation looks like a power series. The solution looks like a power series. I am going to differentiate the power series so that I can plug that expression into the differential equation. Now, when I do this differentiation, we follow the power rule. So I bring the power out front and reduce the power by 1. It's just the normal power rule, except I'm doing it to an entire infinite polynomial at once, right? As we just think about this as being a polynomial, a naught plus a1 times x plus a2 times x squared, and so on. Okay, now, what happens if I take the derivative of a naught with respect to x? It's 0, right? Because that's a constant. Okay, so that's why the series starts at 1 now and not 0. Because that term was destroyed by the differentiation. When I take the next derivative for y double prime, the same thing happens. Okay, now what we do is we plug this in. Okay, so we plug in our series expressions for what's going on here. All right, now I have 2 goals that I need to accomplish. I need to manipulate this expression so that everywhere, all of the sums, all of the series have xk in them, x to the k power. And then after I do that, I need to adjust as necessary the series and the way that they're written down so that all of the summations start with the same index value. So what that looks like here is I need this index to go up by 2 in order to make it x to the k power. That means that the starting value for this series is going to go down because they move in opposite directions. Okay? So I'm going to have the sum from k equals 0 to infinity. This goes up by 2. This goes up by 2. This goes up by 2. And this goes up by 2. Make sense? Okay. The other one we can leave alone. Whole thing equals 0. Now, in this problem, at this point, we have gotten lucky because these already match. That will almost never happen. Okay? But if they didn't match, what you would do is you would pick the one that's the biggest and then peel off terms from the other ones until they all start at the same thing. Okay? Once they all start at the same thing, you rewrite the expression so that it looks like this. Make sense? Okay, now, the next step in this is to try to figure out what the values for these coefficients are, because that's going to tell us what the series looks like. Right? This thing is a polynomial, right? Now, this equal sign says that that's polynomial is equal to 0. When is a polynomial equal to 0? Huh? Okay, that's not wrong. Okay, if I have a polynomial that is identically equal to 0, what's the only way that a polynomial can be identically equal to 0? Meaning equal to 0 everywhere. What's a polynomial have to look like? What does the formula for the polynomial have to look like? Everything has to be 0. Right? So that means that each of these must be 0. And if that's true for every single value, what it allows me to do is write down this expression, which gives me a relationship between, set it equal to 0 and solve for a sub k plus 2. This is known as a recurrence relation. Okay? And this recurrence relation allows me to determine the value of later coefficients based on the value of previous ones. Okay? In this particular example, and this is worked out on the online notes, and I'd like to everyone take a few minutes to go through and take a peek at this so that we can do more interesting examples next class. What will happen is we don't know what a sub 0 is. So we're just going to take a sub 0 as a fixed but arbitrary number. Okay? And I can figure out what a2 is in terms of a sub 0. And because my relation here skips by 2's, the numbers that I get from this pattern are all even, the even ones, right? And then I do the same thing with A1. I don't know what A1 is, but I can use A1 to figure out A3, A5, A7, and so on. It turns out that they form nice patterns. That sometimes happens, sometimes doesn't happen. But once I do that, I can write out two separate series expressions where one of them is all the stuff with the A naughts and the other one is all the stuff with the A1s. And it turns out that all the stuff with the A naughts is Y1 and all the stuff with the A1s is Y2. So I get two members of a fundamental family of solutions, and then I can use that to express the solution to my second order linear differential equation. Okay, and so that's going to be how this works out. It turns out that the functions of this example are sine and cosine because those are two functions that are equal to their own second derivative, which is what this condition says, right, for the differential equation. Okay, so it all works out. All right, so take care, everybody, and we will see you next time.